Okay. Now, so our acceleration vector for this thing would be 6 meters per second squared times I plus 0j. Okay, what's our velocity function then? Well, you're going to integrate the acceleration. You're going to get 6 meters per second squared times t, and then you're going to get some integration constant, which we can identify with the t equals 0 velocity, v0x. And that's going to be your velocity in the I direction. And in the j direction, you're going to integrate 0, j, and you're going to get a constant times j. But we're going to pretty much always set the coordinate system, unless we have a really good reason otherwise, so that the origin of the coordinate system is along the path the object takes down the incline, or up the incline, because we can push something up the incline. And that means that since the path goes through the origin, that the y-coordinate of the position of the object is always 0. So Vy, we get an integration constant on j, which we identify with the t equals 0 velocity, v0y. But v0 is 0 since there's no velocity in the y direction. And what I just told you was why there's why your next constant is 0 in the next integration. The reason the constant here is 0 is simply because you have no motion in the y direction. So the velocity is always 0, so the initial velocity in the y direction is 0. So your velocity is just this function multiplied by I. And that's a velocity function. Okay, you integrate that and you get what? You get an x0 plus v0 xt plus 3 meters per second squared times t squared. Obviously v0 x integrates to v0 xt. 6 meters per second squared times t integrates to 3 meters per second squared times t squared. And the arbitrary integration constant will be identified with the t equals 0 position, which we call x0. So right there's our r function, okay, our position function. And you use a different notation for it, but that's like an r of t, a v of t, and an a of t function. And this, of course, is useful in physics, and most engineering students to whom this is pretty much addressed are also doing multivariable calculus or vector calculus at the moment, and probably, depending on how the two courses proceed, and what the pace is, it's not unlikely that you're also studying the r of t, v of t, and a of t functions in multivariable calculus. Okay? So that's just a little tie-in, but it's also a broader picture of the way you can model motion. Okay? And a picture that can be extended to 2 or 3 dimensions.